needs to go from here and from there, but now well, now it was told that there is 15 meters is the length of the pipeline from here to here. But if there is another 15 meters from here to here, then you should take that account as well. So it depends.
Oh, okay. Okay, thank you.
Okay, Maxim asked that can you show the last part one more time? Yes, do you mean by last time this one? Yes, okay. So it's this component losses when the flow goes through the valve, no matter which way it goes, every time there are losses. And like I told, now I just decided that we need to follow this control C plus. So we want to follow from P to A, that how much losses happens when the flow goes from this point to here. And that was able to find out pretty simple from the question paper. So it is told here that flow goes through the directional valve, which delta PQ characteristics are presented below. So this table here. And like I told, I wanted to study the flow, that what kind of losses happens when we go to P to A. So it is this curve that I'm interested in. And the flow rate in the system is 50 liters per minute. And we just need to find out the place where this 15 liters per minute and this P to A curve will meet. And the crossing point is here, if you see my mouse cursor. And if we would make an horizontal line, we would meet somewhere around here, a little bit less than 2 bars. And I just estimated then this time that it is 1.8. Is it clear now? Okay, no problem. All right. Well, a little bit more questions about this circuit. This was not asked, but if you would have a pressure meter here just before the tank, what it would show to you? What would be the value in that point?
Excuse me, your value for what?
For pressure, if we have a pressure meter, a manometer here, measuring that how much is the pressure in this hydraulic system just before the tank.
But we should calculate the pressure in the system, or do we know the value for the pump?
I think we don't need to calculate anything. What is the pressure of the tank? In this hydraulics assignment that you did, I asked you to put these pressure meters in a couple of places of the system. Did you study what kind of numbers there were? Okay, Dan has put an answer in a chat that 0, and this is correct. It is only atmospheric pressure there. So the pressure, the manometer would show us 0 bars because we don't have any pressure in a tank. It's not the pressurized tank, but the pressure is formed here in a pump, and when the oil comes back in a tank, the pressure is 0. But what if we would have a manometer?
So the reason is because we are in like atmosphere or something?
Yeah, it's always like that, in a hydraulic system, the oil reservoir, meaning hydraulic oil tank, they are not under pressure in a normal hydraulic system. It's a completely different thing compared to pneumatics. In pneumatics, the tank has pressure, but in hydraulics, the oil is in 0 pressure there, and the pump is just sucking the oil and making the pressure.
Okay.
But what if, well, now we don't need the specifications in this system, but and we can't say the exact value that how much it would be the pressure here, but what part it would consist if you would need to find out that how much pressure we have here, how would you do it?
So we know the flow, and we also can find the area of the rod, right?
Yes.
And from this we can, I guess, well, flow maybe is not needed, but the speed is needed, and the area.
And then what would you do with this information?
Well, don't have the clear answer yet.
Well, basically you would do the same thing that we did now. You could calculate, if you would know what is the length of this pipeline, you would know how many these junctions or corners you have. You could calculate the losses in formed parts, and also you would need to calculate the losses or find out the losses when the flow goes from P to T. So there would be all these 3 parts, and then in this point you would see the pressure of the losses here.
So which just subtract losses.
Sorry?
And just subtract losses. So
kind of. So I mean, if you have no losses or 0 bar here, but in here, if I just put something, I will just put 5 bars. This is not a calculated value. This is an estimate. And it consists of this pipeline losses, it consists of this formed part, it consists of this component losses. But if we would have a pressure meter, manometer here, it would show us something like this. So in here, 0 bar, and in here, just after the cylinder, something like 5 bars. Okay, and I will continue this. What if we still have an 1 manometer over there? What part it consists of?
It's not really clear for me. How did you get the 5 bars value?
This 5 bars, I didn't calculate it at all. I just made a very rough estimate that if in other side we had this 6.4 and we have a little bit less flow here, which means that we have a smaller speed of oil here, then the losses between this point and this point could be a little bit less than this value, and I just put it here. Maybe this was not a smart way to do, or not the correct way to do, but I just wanted to put some value here now.
So that doesn't mean that we have zero bars in the tank because of the losses?
No, not because of the losses, but in a tank, in a hydraulic system, you never have any pressure. This is a fact.
Yeah, okay.
There can't be any pressure in a tank. The tanks are designed so that they
if we think that we would have 15 meters of the pipeline also here, and we have some of these corners here, 1, 2, 3 in my drawing, and the flow needs to go from P to T. So we have all these same parts, but the values would be slightly different. And we get some number which I didn't now calculate at all. Like I told, it was just a very, very rough estimate here that there is some value, and it's roughly 5 bars. It might be a little bit less or a little bit more, but this is the value very roughly told.
Okay.
So now I'm just trying to show you and understand that how these different how the pressure behaves in a different places in the hydraulic system and how it consists of. So don't put too much effort to this exact 5 bar value. It is just, it doesn't matter if there is a 4 or 6 or 3. I just put some value here, and the important thing is to understand that here you have 0, but all the time when you travel from the tank to a system, your pressure is raising. And now, if we have an actuator in a return line and we see the pressure here, why there is this pressure, it's because of the losses of this return line. Okay, so let's continue. Now we know that, or I decided that now there is 5 bar. And then if we still have a manometer here just before the cylinder, and now let's imagine that we need to push some load, and we need to have 100 bar for pushing load. So we have such a heavy load that we need to have 100 bar in this chamfer so that we are able to move the load. Okay, is it clear so far?
Could you repeat this part?
Sorry?
If you could repeat this part.
So I just put it a load here, and I decided that the load is such a heavy load that we need to have 100 bar pressure so that we get enough force to move the load.
Oh.
And now if we have a look at this pressure meter here, what would it look like? It would be 105 bars. Because there is this 100 bar, what we need to push the load. And we know that there is this losses 5 bar here. So we need to have 105 bar just before the cylinder.
Excuse me.
Yes.
So just for clarify, so the bottom right parameter is only 0 bars,
Yes, this is always 0.
and the top on the right, they are equal to the losses to the way back to the tank.
Yes, this is equal to the losses of this line.
Oh yeah, thank you. Thank you.
And then in here, we need to kind of have this value and this value. So in this example, it is 105 bar. And then if we still have 1 manometer here in the bottom, now it is this value plus all the losses what we had in this pressure line, which we calculated in this case in an exact way, which was 6.4. So we get here 111.4 bars. Because it was this value plus this value.
So you always have to look from the tank to the pump?
Yes, yes,
Okay.
it's the easiest way. All right, so does it now make any sense?
Just one more question. So, for the pipe to the cylinder, at the pump to the cylinder, they have to suffer a lot of pressure, and on the way to back to the tank, the pipe doesn't have to suffer a lot of pressure.
Yeah, yeah. If you have an open connection so that you don't have any kind of speed control here, then there is not so much pressure in this line. But if you would have a system something like this, that you would have an orifice here, then it would mean that the pressure here would be bigger, because the operating principle of this orifice is such that it won't control the flow before the pressure rises here. But now in this example, there was no orifice at all, so then the pressure is very small in this return line. There is nothing else than the pipeline losses and component losses that will form the pressure.
Yes, it's clear. Thank you.
All right. So that was this question, and now it's time to go through this hydraulic fluid material. So one moment. Okay, maybe before I open the PDF, I could ask you a question that what do you think that what are tasks of the fluid? So what different tasks hydraulic fluid needs to do in a hydraulic system?
Might be calculate the losses and calculate the pressure that we have to need in the hydraulic, and if there are some changes in velocity and height of the fluid, we have to calculate some losses more. And
okay, but now I didn't mean that about the calculations, but I mean in general that why there is this hydraulic fluid, what is the function of the fluid in this system, what are the different things that the fluid is needed for?
Actuation? Or anything
Yes,
like that?
yes. So I think this is the most important thing, to transmit the power from point A to point B. This is the reason why there is hydraulics, the most important thing. But then it has also some other tasks.
I wonder if it somehow can be applicable for cooling.
Yes, yes, definitely. This is one thing. It will transmit the heat from the system to a tank or to a cooler, exactly. And then something else still.
Sometimes push and pull, like some kind of loads.
Yes, yes, this is kind of the this first thing, the most important thing in hydraulics, meaning it will transmit the power.
Okay.
Yes, but there are still some tasks that it will do in addition to this one and cooling. Can you figure out or guess something else?
Transport, maybe.
Just lubrication, maybe. I don't know.
Yes, yes, lubrication is the one thing, because there are moving components and you need to lubricate them, and I think prevent some corrosion at the same time. There is still one thing which is pretty important. And it is related to filters.
Cleaning, in a way, like.
In a way, yes, because all the dirt particles that comes to the system from the components or from outside air, the fluid is used to transport all the dirt particles into the filter, and then they are taken out from the system. So I think these were all the main parts. So let's see. So this is the hydraulic fluids presentation. And if we talk about this task of the fluid, so in theory, no matter what fluid it is, it could do this basic thing, so transmit hydraulic power. But because there are other demands for the fluid, then any fluid can't work as a hydraulic fluid. And these other tasks, what you told me and what I told you, they are mainly connected to system service and maintenance. And also it is important to understand that there are many different hydraulic applications that can vary very much. And that means that also the demands for hydraulic fluids are very different. You can think about, for example, an airplane or paper mill or forest tractor. So what do you think that what is the easiest case? Airplane, paper mill or forest tractor in a hydraulic fluid point of view?
It's not very clear what is easiest, the less complicated?
Yes,
Or?
yes. That what has not so much demands or the easiest demands for hydraulic fluid?
May I say all of these cases are equally complicated and have different requirements?
Well, not fully.
I think paper mill, maybe.
Yes, I agree. I think the paper mill is the easiest. And why do you think it is paper mill?
It's stationary, doesn't really depends on the environment because it's
exactly.
maybe more or less same. And
yes, exactly. This is the case. So in paper mill, you have, even though it might have very heavy pressures and high loads and in that way a demanding system, but still the conditions, operating conditions are always the same. Of course, there are other problems, but in a way it is the simplest. Then if we think about forest tractor or aeroplane, there is a huge difference. There can be a huge difference in the temperature when they operate. A forest tractor, it's outside at the moment, it can be minus 20 degrees. And in the summertime, it can be plus 20 or plus 30 degrees, the environment temperature. But this is still a little bit easier because you are able to change the oil so that you will use a different oil in wintertime and different oil in summertime. But if we think about aeroplane that has also some hydraulics, it will fly on the sky and the temperature is, I don't know how much, minus 50 degrees maybe. And then it can land on a place where it is plus 50 degrees. So there is a very huge difference in the temperatures, and it causes also huge demands for the hydraulic fluid, what they use in airplanes.
Should we also take into account the difference in pressure? It's not really related to fluids, but rather to the system itself?
You mean if we talk about aeroplane, for example?
Yeah, because we are climbing higher and the atmospheric pressure is getting lower.
Yes, it's true. If you want to calculate the things very accurate way, then yes, you should also take account these different pressures. It is true. But I still think, well, I have to say that I don't know aeroplane hydraulic systems so well, but I think that those pressures what we use there, they are so much higher compared to the small change of this environment pressure that they don't really have any effect in real life. In theory, of course. But like I told, this is not my special area, the airplanes, so I can't say it for sure. So basically, these were once again the tasks of the fluid. The most important one, then lubrication, cooling, corrosion protection, dirt particles transport to the filter. And in some cases, this might be a voltage. thing or unwanted thing that hydraulic systems tend to damp a little bit. There is always a small amount of air inside hydraulic fluid, and it will create some damping, not much, but a little bit. And the hydraulic fluid can be used for signal transmission, just in a similar way that you can use electricity or pneumatics. You could also transmit hydraulic signals and use them to move valves, for example. Well, this is of course not so important nowadays, but still possible. Then if we have a look at the most important features or characteristics that we need to know when we select hydraulic fluid, the most important is viscosity. It has a great effect to efficiency of the system and also to lubrication features. And it is very important to select a suitable viscosity oil in a system. And you need to know the ambient temperature and operating temperature so that you are able to select the correct viscosity. If you select the wrong viscosity, it can cause, well, it says now here discavitation and a pump failure, and it can also cause some other problems. There can be leakages if the viscosity is too small. Did you find out what discavitation means?
So this is more or less negative effects of, I think, air bubbles inside the fluids, which
Yes.
might damage components. For example, it's very widespread in marine industry and with these propellers underwater.
Yes, yes,
Yeah.
true. And the phenomenon, I think it is here in the last slide. So it starts in a situation that you have some pressure in a system, and inside hydraulic fluid, like I said, there is always some amount of air inside the fluid. And then if you have a sudden pressure drop, so that the pressure goes very suddenly down for some reason in the system, if there is a very narrow gap or some other reason in a pump line, those bubbles come out of the oil. So the air comes out of the oil and form bubbles. And then when the pressure raises up again, those gas bubbles will collapse and they will generate pressure shocks and high local stress, and they can remove some small particles out of the surface and then cause a failure. And normally in hydraulics, where you see this cavitation, it can be in these control edges, which means these narrow gaps inside a pump or inside a hydraulic valve. And also it can happen in pump suction lines. So the line between a tank and a pump, you have to make sure that it is big enough so that there is not too much under pressure below zero. Yes, so quickly told that was the cavitation, and then let's go back here. So viscosity, there is an ISO standard that puts hydraulic fluids in different viscosity classes. You can read from fluid that is it ISO VG10, 22, 32, 46, 68, or 100, or there are several more, but this is the most common ones. And what does the number here means? This means that what is the kinematic viscosity at 40 degrees Celsius temperature of this oil. So if you see an oil that is called ISO-BG32, you know that its kinematic viscosity is 32 square millimeters per second at 40 degrees temperature. And the standard gives limit that what it can be in minimum and what it can be in maximum. So for instance, this one, the minimum value so that it is still accepted according to the standard is 28.8 and the maximum value 35.2. But roughly in the middle is this number.
So that's the kinematic viscosity. I mean,
Yes.
it's 32 square millimeters per second.
Yes, yes. So this is the value what you have used in the calculation. I have told that kinematic viscosity is, for example, 40 times 10 power of minus 6, which is the same thing as 40 square millimeters per second. I just have made the unit conversion to square meters per second so that it is in a correct format to use in your calculations. And how you are able to measure the viscosity from certain oil, you can use this kind of device. There is an inside the pipe there is some liquid that you want to test, and then there is some ball that you drop inside the liquid, and then you measure that how long time it takes that this ball drops from certain height down. And the viscosity is not a constant value. So it's told here that this number, it works in a certain temperature. And when the temperature is changing, also the viscosity value is changing. And there is several different oils in this table. And you see these lines here. And I don't know how well you can see it in your computer, but it tells here that this is ISO-BG 15, 22, 32, 46, 68. So basically the same things what are in here. And this is how you see that there is this 40 degrees and there is the kinematic viscosity. But the same oil, when the temperature is changing, the value for viscosity is also changing. So it's not constant. And actually, I think now it's good time to talk about that how much the viscosity changes when the temperature is changing. There is also a factor in hydraulic fluid that is defining that what is the slope here. Is it the correct word, to slope?
Yes, the slope.
Yeah. So how big is the slope? And it is called viscosity index. So it is a reference value for this viscosity temperature characteristic. And in this chart, there is 3 different oil, and they all have same viscosity. So in 40 degrees Celsius, they have exactly the same viscosity value in this point here. But since they have different viscosity index, the viscosity is changing in a different way when the temperature is changing. So this one, which is called here VI3, has the highest viscosity index. It means that the viscosity is changing not so much compared to the other oils here. So you can say that this is the best oil. because it is the wanted situation. You would like to have as constant viscosity as possible. Now, if you still think about this aeroplane, it needs to operate in this -40 temperatures, and it needs to operate here in well, maybe not 80 degrees temperatures, but here in 60-degree temperatures. So you would like to have the line as horizontal as possible. So you need to have a high viscosity index, which means that, of course, you need to put some additives on the oil, and it makes it more expensive and maybe more harmful, the oil, compared to standard oil. Then you might have noticed some engine oils that have some marking, for example, SAE 10W or SAE 30. And if you have ever figured that what they mean, basically it means the viscosity of the oil. It is just a different standard to to give this viscosity. So in hydraulics, we use this ISO-VG standard, but in engine oils, very often are used this SAE viscosities. But there is some comparison between these values. And also you see here some areas of application. This is just a roughly estimation. So what are the fluids, what are used in normal temperatures? They are these one, 32 and 46. Then if you have in cold conditions, you operate in a very cold conditions, then you use these fluids, which have a lower viscosity, and very hot conditions, you use this kind of fluids. But these are the most common ones, 46 and 32. So how you should then choose the correct viscosity for your system? An ideal range is somewhere between 15 and 100. And there is some absolute lower limit, which very often is told it is 10. So you should never run the system so that the viscosity is less than 10. And there are also some upper limits, so that you are not able to start a system if the viscosity is too high. And why there are these limits? If you have too low viscosity, there are more leakages, and it might be that the lubrication is not good enough, and it can cause a failure for some hydraulic component like a pump or valve. And if the viscosity is too high, you get more friction, you get more pressure losses, you get more heating. And if you do a cold start for hydraulic system, it might cause this cavitation phenomenon to a pump, and it can cause a breakdown for the pump totally. It is not wanted situation. So you should know the working temperature of the oil, and then select such an oil that the viscosity would stay between this area. Then everything is fine. I could show you quickly here if we go to hydraulic components, and we have this Bosch Rexroth catalog. And if we have a look at the valves, for example, directional valves, spool valves, direct operated, and then I will open a data sheet. What it is told that what kind of oil and what kind of viscosities are okay. Let's have a look. Hydraulic fluid, see table page 6. Viscosity range from 2.8 to 500 is okay to this component. So for this valve, you could accept less than 10 viscosity. And there is a list of acceptable fluids: mineral oils, biodegradable oils, flame-resistant oils, and some classification for them. These ones are accepted. And some suitable sealing materials. So different oil type or different fluid type has different demands for sealings. But anyway, as a viscosity, we got this answer, that if we have this specific valve, this is a range where we can operate. But then on other example, let's select a pump. For example, internal gear pump. And a data sheet once again. Now we have a different viscosity range. It is from 10 to 300. So now this 2.8 is no more acceptable, but it needs to be at least 10 when you want to operate with this pump. And this 300 is no more, let's say, ideal. It says that it works, but in an ideal way, you should be close to 100. So between 10 and 100, I would say there is the most ideal viscosity range, or it can be even more narrow, so that it is from 10 to 50 if you want to have a best efficiency. And also it tells that permissible starting viscosity maximum 2000. So this is a way how you can see that what demands these different manufacturers have for their parts and components.
I have one question.
Yes.
What exactly is the starting permissible pressure? Because the pressure range in the pump is only from 10 to 300, but the permissible starting pressure is up to 2000. So
it was
how does that?
It was
different?
not a pressure, it was viscosity.
Oh, sorry, the viscosity. Why there's some difference?
It means that you're able to start the system in cold condition when you might have this 2000, but then you need to wait until the system heats up, so that when you start to operate the system, you need to have a warmer oil so that the viscosity is higher, or sorry, smaller.
Okay, I understand.
Okay, then I have a list of different hydraulic fluid types: mineral oils, biodegradable fluids, some emulsions, water, and synthetic fluids. And the mineral oil is the most common hydraulic fluid. It's made out of crude oil, or in other words, petroleum. There is a standard that defines the oil itself, and there are different classifications for mineral oil. You saw already in this post-Rex root catalog that there were HL, HLP, and HV, and it means that what kind of additives you have put on an oil so that you can increase some characteristics. So if we compare these three, this is the best one. It has all the characteristics what they have, but still it has in addition some improved viscosity, temperature characteristics. So wait a moment, where was it? Okay, it was not here, but for instance, in there it says permissible hydraulic fluid, HL mineral oil, HLP, and so on. This was for the pump. And for the valve, HL, HLP, HLPD was acceptable. All right. Then there are these biodegradable fluids, which are environmental friendly. They are defined in a different standard, and there are also different classifications depending what is the base material or raw material, what they are made out of it. For example, this HEDG is made out of vegetable oils, for example, like the is it called raps? The yellow plant, what is in the fields, even in Finland, and you can make this kind of oil what you use in cooking, or you can make out of it an oil what you can put on a hydraulic system. And the basic characteristics of these biodegradable fluids, they are very close to mineral oils. They have a good viscosity index, but there are some problems with very low temperatures, like we have in wintertime in Finland. The good thing is, of course, that they are non-toxic if there are no additives inside the oil. But the problem is that they have a fast aging, meaning that the oil loses its properties quite soon and you need to change the oil. But these ones are used, for example, in the forest machinery, or could be used with the forest machinery, because if there is a leakage, it's not a catastrophe if some amount of oil goes to the nature, because it is biodegradable. But to tell truth, still not all machines are using these biodegradable fluids because of two reasons. One is that you need to change them quite often, and you might have some problems with low temperatures. And the other problem is that they are more expensive to mineral oils. And this picture, just a curiosity that normally the forest tractors don't look like this, but they have really built this kind of walking forest tractor. There is a year visible, 2002. It was designed in a Finnish company called Timberjack. Nowadays it belongs to John Deere, big company. But you can see this one in museum at the moment. They built, I think, just one prototype, and they tested and it worked, but it was not so good as they thought, so it just was a prototype. But the walking forest machine has been done 20 years ago. Water can be used as a hydraulic fluid as well. And of course, this is the cheapest option possible. It's not toxic. There is no risk for inflammation. It has a very good viscosity index, which means that the water viscosity remains more or less the same between, let's say, 5 degrees and 95 degrees. But the problem is what happens outside of this range. If we go down to below 0, you know what happens, and you also know what happens if we go below or above 100 degrees. So water can't be used very often, but the biggest problem is the viscosity itself. Even if the viscosity index is good, the viscosity is very low. So you can't use normal hydraulic components if you want to use water as the hydraulic fluid. But you need to have special components. There are special components which are meant for water. And this water hydraulics is used in some industry areas. For example, in food industry, because it causes not so much problem if there is a leakage compared to if you would have a mineral oil. And other industry where it is used is the offshore industry, meaning those, what is the name of this? Is it oil rich, or how do you call this? Devices which are out of in a sea and taking oil out of the bottom of the sea. Oil rich, or how is it called? Anyway, oil rig, yes, exactly. So in there you use water hydraulics because there is no risk for inflammation. Then other fluids which have low flammability, which are used these kind of hazardous areas. There is a list, and once again some codes according to standards. Some of them are oil-water emulsions, some are water-oil emulsions. It means that in this first case, water content is more than 50%, and in this second case, it's less than 50%. Then there are some water glycol emulsions, and then fully synthetic fluids like this HFD. And with these synthetic fluids, you're able to go to very high temperatures, even 300 degrees Celsius, but they are very toxic and also very expensive. Some other features which are important when you select hydraulic fluid. This lubrication, density. Well, density, you really can't do so much for it. It is what it is. And then there is a list of other features which might be important or might be not so important depending what is an application. So then if you are in a situation that you need to choose the fluid type, well, at first you need to do it in an early stage because it has this influence to this component choosing. If you, for example, choose this water, you need to have special components for water hydraulics. But basically, how it is done, the first question is that what is the ambient temperature and what is the temperature range? And based on this information, you find out that what is the viscosity that you want to use and how big viscosity index you need for the oil. And next question is that is there any special demands for oil? For example, that does it have to be non-toxic? If the answer is no, then I think it's the costs that has the most influence, and in many cases then the answer is mineral oil because it's the cheapest one. Unfortunately, this slide is in Finnish and it's not so high quality other way, but I try to explain what it tells here. So there is this viscosity and temperature characteristics, and this is a line that how the oil behaves in different temperatures, so how big viscosity it has in different temperatures. And if we know that our ideal viscosity is here somewhere between 10 and 100, actually it is told here it is much more narrow area. It is something like 10, 20, 35, something like 15 to 35 here. And you can change it to a temperature, which would be an optimal operating temperature. In this case, something like 40 to 55. So that is an optimal viscosity area, optimal temperature area. Then there is an allowed, maximum allowed operating viscosity and minimum operating viscosity. And the corresponding temperatures are here. And then there is still the one value, the maximum acceptable starting viscosity. And with this oil, you see that what is the temperature? Minus 25 degrees. So in this way, if you have selected the certain oil, you are able to give the operating temperatures for the device. Then in this slide, I have just collected some information about changing the fluids. Well, there is not any universal instruction that how often the fluid should be changed, but it might be the case that the machine manufacturer says that you need to change the oil after 6 months, or it might be that the manufacturer of the oil says that this oil needs to be changed every year or whatever. If you work outside, it makes sense that you will change the oils always before winter, because during the operation there might be some water that goes into the oil, and it makes sense to get rid of the water before the winter. And if you have some huge systems like in paper mill or in other industry, in factories, so that you have thousands of liters of oil, it makes no sense to just change the oil every 3 months or every 6 months or even every year. But it makes more sense to analyze some samples of the oil and then make a decision that do you need to change the oil or not. And also it is important to understand that the dirtiness of the fluid, it is not a solution that you just change the oil and the problem is solved. But if you have some dirtiness in the fluid, then you should find out the reason. Where does it come from? You have a problem in filtration. You need to change filters, or you need to find out the source of dirt. Oil changing is not solving the problem. Also, it is important to understand that there are so sophisticated hydraulic systems that sometimes the new fluid that you buy from a shop is not clean enough, but you need to put it in a system through a filter so that it is clean enough for certain sophisticated, for example, servo hydraulic systems. And also a general rule that different fluid types should not be mixed together, but if you have certain oil in a system, you should add the same oil later on. And then a final slide, some things that is important to remember when you handle the fluid and when you operate with the fluid. This oil spray is dangerous because if there is only a tiny hole in a hydraulic hose or pipe, the pressure inside the pipe is so high that the speed of the oil that it comes out of the pipe, it can be very, very high, and it is very dangerous for eyes and also the skin. So you should never try to seal the leakage so that you will put your hand on a pipe where there is a small hole. Then the oil will go inside your hand, and that is not a wanted situation. So also there is a risk for inflammation, and the oil can be very hot. It can cause some burns in your skin, or in some cases it can be very cold. Once again, this example from airplane, so that imagine that it has been in a minus 50 degrees Celsius in the sky, and then it lands in a place where is a very hot temperature, but still it can be freezing. The oil can be freezing what comes out of the airplane. Well, slippery, of course, and long-term skin contact can affect some irritation. And you need to know that some of the fluid are not so good for the nature. For example, these mineral oils. So you should not pour them to a nature, but you should deliver always the oil to some hazardous waste, the places where they took this hazardous waste, to some receiving stations. Okay, now I think that I have told you everything that I wanted to tell you. today and before the exam. Do you have any questions now about the fluids or in general about things or exam?
So the exam is like a multiple choice?
Not fully. There are also essay questions so that you need to type an answer. And also there are some calculations, so you need to calculate something by yourself and then type a number, give a number as an answer in Moodle.
Okay. Okay. So for example, it's only a question, but the number in decimals you have to put with point or a comma, or it doesn't matter?
It doesn't matter. I think this Moodle accepts both of them.
Okay. Perfect.